All right, welcome to The Explainer. Today we're going to take a journey, a really deep one, right inside the building blocks of our entire universe. We're going to figure out the fundamental rules that make everything, well, everything.
So look around you. I mean, everything. The chair you're on, the air you're breathing right now, it's all made of matter. And usually, we experience this stuff as a solid, a liquid, or a gas, right?
But what is all this stuff, really? To get that answer, we've got to shrink ourselves down. I'm talking way, way down, to the atomic level. We have to go beyond what we can see and touch and really explore the invisible architecture of reality itself. Okay, so let's meet the main characters in our story, the components of the atom. It is a seriously tiny world down there, but believe it or not, just a few key players are responsible for, well, all the complexity we see all around us.
So every single atom is basically made of three main particles. You've got protons, which have a positive charge, and then you have neutrons, which are neutral, no charge at all. These two guys are clustered together right in the center, in a core we call the nucleus. And then, buzzing all around that nucleus, you've got these tiny, negatively charged electrons.
And here's the crucial part. An element's identity, whether it's gold or oxygen or carbon, is decided only by its number of protons. That's it. This is called its atomic number, and it's basically a unique ID for every single element in the universe. How we picture the atom has changed so much over the years. It's actually a pretty cool story. We started out thinking it was just this solid little ball. Then came the plum pudding idea, which is a great name. Then Rutherford figured out there's a dense nucleus in the middle. After that, Bohr came along and put electrons into these neat little orbits. And that finally led us to where we are today with the quantum model, where electrons are more like fuzzy clouds of probability. What a ride, right?
Okay, so now that we've met the building blocks, let's check out the ultimate instruction manual for how they all fit together. You can think of it as the roadmap for all of chemistry.
And here it is, the periodic table. This is basically a cheat sheet for the entire universe. It was first put together by the brilliant Dmitri Mendeleev way back in 1869, and it organizes every known element by its atomic number. That proton count we were just talking about.
But the real genius of the table is in the columns. See, it's organized so that elements with similar behaviors are stacked right on top of each other in these groups. So, for example, all the elements in that first column, the alkali metals, they're all super reactive and in a very similar way.
So why is that? Why do they act so alike? Well, it's because they all have the exact same number of electrons in their outermost shell. We call these valence electrons, and they're the real MVPs. They're the ones that do all the work, deciding how an atom is going to bond and react with everything else. All right, let's shift gears and zoom right into the atomic core. We're going to dive into that tiny, dense nucleus we mentioned before, because this is where we find the most powerful force in all of nature. Okay, so here's the puzzle for you. The nucleus, remember, is jam-packed with positively charged protons. But wait a minute. We all know from basic physics that like charges repel each other, right? They should be pushing each other apart, violently. Just imagine trying to force the positive ends of two super strong magnets together. It's impossible.
So that brings up a massive question, doesn't it? If all those protons are constantly trying to fly away from each other, why do atoms even exist? Why doesn't the entire universe of matter just, fly apart? Well, the answer is something called the strong nuclear force. You can think of it as a kind of cosmic superglue. Now, this is the most powerful of the four fundamental forces in nature. But here's the catch. It only works over incredibly short distances. But in that tiny, tiny space inside the nucleus, it's about 100 times stronger than the electromagnetic force pushing those protons apart. It just completely overpowers that repulsion and locks the nucleus together. Incredible, right?
So you've got this delicate dance, this balance between that push-apart force of electromagnetism and the pull-together force of the strong nuclear attraction. And that balance has some absolutely fascinating consequences. It's not always a perfect, stable harmony.
See, because neutrons are neutral, they don't affect the atom's charge, you can actually change how many neutrons are in the nucleus without changing what the element is. When you do that, you create different versions of the same element, and we call those isotopes. So same number of protons, which means it's the same element, but a different number of neutrons.
A perfect example is hydrogen. Regular old hydrogen has one proton and that's it, no neutrons. But if you add a neutron, you get something called deuterium. Add another neutron and you get tritium. They are all still chemically hydrogen. They just get a little bit heavier each time. This whole idea of shared properties helps us categorize what you could call different nuclear families. So we have isotopes, which share the same number of protons, but you can also group atoms that have the same number of neutrons. We call those isotones. And you can even group them by their total mass, which would be protons plus neutrons. Those are called isobars. Kind of neat, right?
So, at the end of the day, that proton-to-neutron ratio is everything. If that balance is off, the nucleus gets unstable. It becomes radioactive, and it'll try to get back to a more stable state by spontaneously decaying, and when it does that, it shoots out energy in the form of radiation. So, why does any of this matter to us? Why care about this tiny, invisible core? Well, because understanding this delicate balance is the key to unlocking an absolutely unimaginable amount of energy. It turns out, by intentionally knocking a heavy, already kind of unstable nucleus like uranium off balance, we can trigger a process called nuclear fission. We are literally breaking that cosmic superglue on purpose.
So here's the play-by-play. A single neutron comes in and smacks into a heavy nucleus. That impact causes the nucleus to split apart. Now this split releases a ton of energy, but, and this is the critical part, it also releases more neutrons. And what do those new neutrons do? They go on to hit other nuclei, which split and release more energy and more neutrons, and on it goes. You get a self-sustaining chain reaction.
And that chain reaction? That's the basic idea behind nuclear power plants. We control that fission process very carefully to generate an incredible amount of heat. Then we use that heat to boil water, create steam, and that steam drives massive turbines to generate huge amounts of electricity. And the best part? It's all clean, carbon-free power. So think about where we've been, from the simple states of matter that we see every day, all the way down to the immense power locked inside the nucleus. This journey to the center of the atom just reveals these elegant, powerful rules that govern our entire reality. And it really makes you wonder, doesn't it? If this much power comes from just splitting things apart, what other secrets are still hiding in these fundamental building blocks just waiting to be unlocked?